Hello everyone. In this video, I will explain one type of modulator which is used to generate AM signal, and especially double sideband full carrier type of signal by using something called as a switching modulator. Now, in this switching modulator, this is the diagram, circuit diagram of a switching modulator, where I have used a diode as a switch. That's why it is called switching modulator. And this diode is actually working in the linear region of its input characteristic. So we should bias in such a way that it should operate always in the linear portion. That means it will either turn on and off depending on the input signal. Now here, since we have to modulate and we have to change the amplitude of this carrier signal proportional to the amplitude of the message signal, both signals are given in series in this particular circuit. So my V1 of t is nothing but it is the sum of these two signals, and that is given as input for this. And we have to operate this diode as a switch. In the output of this circuit, I will get a V2 of t, the output of the diode, and that is given to the band pass filter. Simple LC parallel resonant circuit or a band pass filter, it is tuned to the carrier frequency, remember. So we have to design this tuning circuit to allow only the carrier frequency. It's a narrow band pass filter which allows only the signal which is having a frequency of FC hertz. Now, coming to the equation part, time domain, the frequency domain representation, how exactly it produces the AM signal, that we have to understand now. So as I told here, the two signals are given in series. That means V1 of t is nothing but it is M of t, my message signal, plus AC cos omega ct or AC cos 2 pi f ct. Okay, where always the magnitude of this M of t, the instantaneous voltage of the M of t, should be very much smaller than AC. This is one of the very important conditions which we need to satisfy. Now, what is the output? I said already that it's a switching modulator where the diode is used as switch. That is either it is turned on. If when it is turned on, the input signal is allowed to pass to the output. If the diode is off, the switch is off, the input is disconnected from the band pass filter. So mathematically I can represent something like this. We have to design such a way that the output V2 of t is equal to the input signal. The output is connected to the input through an on switch only when C of t is more than 0. That is during the positive half cycle. During the positive half cycle, the carrier signal is more than 0. If carrier is on the negative side, negative half cycle less than 0, during that time V2 of t should be equal to 0. That is, V2 of t is equal to 0 means the diode should be off or open circuit. When the diode is open circuit, the input is not connected to the output. When a diode is acting like a closed circuit, that is during when C of t is more than 0, the output is equal to the input. So this condition we need to satisfy when you are working with this AM modulator. So what I can say over here is the diode is turned on and off depending on the carrier signal voltage. During the positive half cycle on, during negative half cycle it is off. So that means I can represent this the equation, the relation between the output and the input using another method, that is V2 of t is equal to V1 of t multiplied by some series of pulses, that is Gp of t. So this equation and this equation are almost same. Where Gp of t is nothing but it is series of pulses what I have shown over here. Okay, and this pulse is on when C of t should be greater than 0. Pulse is off when C of t is less than 0. I will show you this in the next slide. Now, by substituting V1 of t in this equation, that is this particular term, what I'll get V2 of t is equal to M of t plus AC cos omega ct into Gp of t. Okay, now just look at this. Whatever the condition I said, we have to satisfy to get the same equation in terms of Gp of t. Just look at this. This series of pulses is nothing but it is Gp of t, and this pulse is on when C of t is more than 0, above 0. When C of t is below 0, this is your carrier signal. Let us say this is the carrier signal. When C of t is less than 0, the pulse is off. If I go back to the equation here, if C of t is more than 0, during that time Gp of t is equal to 1. Right? 1 multiplied by V1 of t is V2 of t. That is V2 of t is equal to V1 of t when Gp of t is equal to 1. And this Gp of t is equal to 1 only when C of t is more than 0. If C of t is less than 0, Gp of t is 0, that means this component will be 0, that time V2 of t is equal to 0. That means I will get back the same equation whatever I have given here for a switching modulator. Now, we will derive an equation in the time domain now. Then later we will go to the frequency domain. So we have used the Gp of t, okay, which is for this particular now values and all here, that is minus t naught by 4 plus t naught by 4 with the magnitude equal to 1 equally divided between the origin here, right, 0. Now for this particular case, I can write a Fourier series expansion of such Gp of t given by this particular equation, that is 1 by 2 plus 2 by pi summation. This n, the value of the n goes from 1 to infinity, minus 1 to the power n minus 1 divided by 2n minus 1 cos of 2 pi fct, the carrier frequency, multiplied by 2n minus 1. And if you substitute different values of n, I can expand something like this. Is half of 2 by pi cos omega ct, that is 2 pi fct for n equal to 1. Okay, for n equal to 1. For n equal to 2, this term I will get. For n equal to 3, I will get this particular term. Okay, so this is what I'll get. So if when you multiply, I will get this particular equation. That's it, half of something. So that m of t AC cos 2 pi fct, okay, is multiplied by the Gp of t. I will get V2 of t here. So that's V2 of t is equal to V1 of t multiplied by Gp of t. Okay. Now, considering only the two terms, I will know this particular V1 of t multiplied with this, that is half, and 2 by pi cos omega ct. So these extra terms, whatever I had up to infinity, I call them as the harmonics, the higher order harmonics. So I will neglect in the derivation all the higher order harmonics. I consider only this half plus 2 by pi cos omega ct, because anyway all the higher components will be eliminated by my band pass filter, because it is used to tune only the frequency component of fc hertz. Now, so I consider only this portion and this part, half plus 2 by pi cos omega ct. So I consider only those parts here. Then I multiply. Okay, I will get this particular equation, right? I apply a cos square theta rule. Fine. So I get a half m of t, and this particular component, this term AC by pi, it is cos square theta is 1 plus half of 1 plus cos 2 theta. So that I will get. Then I substitute over here. Okay. Now, if I use a band pass filter will eliminate further any signal which is having. Let us say I just draw the filter characteristic over here. See, just give me a second. Okay, anyway, this is a band pass filter which has the response centered around FC. That is, it is a narrow band pass filter which allows only the components up, well within FC hertz. That means this component which is so this component which is m of t, original signal m of t, message signal m of t, will be eliminated by the band pass filter. This component is m of t multiplied by cos 2 pi fct, which is very close to fc, right? So this component will be allowed by the band pass filter. This component is having this is unmodulated carrier which is having a frequency of fc hertz. Anyway, this will be allowed by the band pass filter. AC by pi is a DC function because there is no cost associated with this. It's a DC term. Anyway, the band pass filter will eliminate this. This is the 2fc term. This is AC by pi cos 2 pi 2fct, which is equal to 4 pi fct. It's a 2fc term. Anyway, the band pass filter will eliminate this also. So this term and this term will be eliminated by the band pass filter. So in the output of band pass filter in my circuit, which I showed earlier, in the circuit, in the output of the band pass filter, I will get only the terms, this one and this term. So it is 2 by pi m of t cos 2 pi fct, this part, plus AC by 2 cos 2 pi fct. Only these two terms I will get. Fine. In this case, I will take AC by 2 cos 2 pi fct common. In that case, AC by 2 cos 2 pi fct I have taken out. We get only this particular term, that is 1 plus 4 by pi AC m of t. This term I will get. Now I will compare this equation. Just give me a second. Okay, so I will compare this equation with the standard equation of AM, because we have to finally we have to cross check whether we have got this double sideband full carrier signal or not. That is conventional AM signal. So I have taken a standard equation of AM, conventional AM. I will compare this with this equation which we got in the output of the band pass filter. Now let's compare this. Instead of AC, I have AC by 2. No issues, no problem. 1 here a m of t, I have a m of t, and this is nothing but, see, 4 by pi AC is nothing but, it is KA. And cos 2 pi FCT and cos 2 pi FCT is matching, right? So this is your double sideband full carrier signal. Now, we will go to the, this is in the time domain. Now I will go to the frequency domain. So I take a Fourier transform to this equation, whatever I have got earlier. Same equation which I have got here, right? This is the equation. So now if I take a Fourier transform to this equation one by one, the last equation over here, okay, is a half m of t, is it is half of m of f, right? Here m of t is multiplied by cos 2 pi fct, that means in the frequency domain, m of f should be shifted by fc. So what we get, it is 2 by pi I have, it is 2 by 2 pi because it is half of something, so that 2 cancels, 1 by pi, m of f minus fc, m of f plus fc. This is the term I get because of this term in the time domain. Here I have a simple cos function, that means it's a delta function, correct? AC by 2 I have already the amplitude, here it is AC by 4, delta of f minus fc plus delta of f plus fc. Here I have a DC term, okay? So DC is represented by a delta function in the frequency domain, it is AC by pi into delta of f. What about this? It's the 2fc component, a cos signal, that means it's a delta function at minus 2fc and plus 2fc. So this is AC by 2 pi, delta of f minus 2fc plus delta of f plus 2fc. Now we will let us draw all these, the spectrums in the frequency domain. So it is half of m of f, that's what. This is your original spectrum, m of f. This is at 0, f equal to 0, m of 0. So this component is represented here. Just look at this. It is half of m of 0. That's what I have taken. This is the m of f. Now what about this? 1 by, with a magnitude 1 by pi, the m of f is shifted by minus fc and plus fc. So I have a m of f, okay, at minus fc and plus fc. So it is minus plus fc and minus fc. I have a m of f with a magnitude equal to 1 by pi here, centered around fc. What about this? We have a delta function at minus fc and plus fc. It's minus of minus fc. Anyway, so I have a delta function over here and on the negative side also. This is a delta function at the origin, right? Delta of f at 0. So there is a delta function at 0, which I think is not shown over here. There should be a delta function. Now, this one is a delta function at minus 2fc and plus 2fc. So we have a delta function at 2fc and minus 2fc. Now what I will do is, I design a band pass filter which is used to allow only this component. So this is the ideal characteristic of, say, band pass filter. This is the ideal characteristic of band pass filter. So I will draw one band pass filter characteristic curve over here, which is used to allow only this component. Okay, that is 2 sidebands and 1 carrier, unmodulated carrier. So hence we get a conventional AM signal by using switching modulator. Okay, so thank you for watching this video.